Now, some interesting applications of autoencoder. Since you don't need labels, what you can do is you can take your input image and make it noisy. Deliberately add some noise to that image. Okay, and then again, learn the latent code, use decoder to reconstruct. So when you're reconstructing, don't reconstruct the noisy image. Reconstruct the original image, which was the clean image, because you already have that clean image. Right? You use that clean image to get this noisy input. And just train this autoencoder. And then what will happen is it will be kind of a denoiser for you. So during test time, if you have some image which is kind of noisy, so what this autoencoder will do is you will feed in the noisy image, but it will be able to recover like the clean image for you. And for that noisy image, you might not have the clean image. Right? You might just have that noisy image. For example, like some of your photographs, old photographs, which were captured maybe from decades old photos, which are noisy, not very good quality, you can just pass it to like this encoder and it will give you the clean image. And in fact, this is actually used like these days. There are a lot of applications. I think in Adobe Photoshop, you should have that. So very simple idea, right? And you don't need any labels for this, and very, very powerful. And again, this could be a very good course project for you. So I have a couple of these interesting applications of autoencoder. As I said, like this is a very, very simple lecture, but I think a very interesting one. Now in this one, what you can do is, let's say you have a lot of colored images, but deliberately you can just convert them to grayscale. That's pretty straightforward mathematical operation, right? And what you can do is you can train your autoencoder where the input is a grayscale image, but the output is a colored image. Because you already have the colored image during training, you can just train that network. So what that network is actually doing, it's taking in grayscale image, creating colored images. And because you have the ground truth, you can easily train that using a lot of samples. And at the end, when that network is trained, again, you can take out like your photos from, let's say, 80s or 90s, when we didn't had colors, right? And just pass that image to that network and it will just color that image for you. All right, another interesting application. This is a little complicated, so bear with me. Here, the idea is you have like a lot of clean images, right? Where, so anomaly is something which is kind of something unusual, which you're not expecting. For example, in this scenario, if this is a walkway, right? You should not have cars here. For example, you should not have this golf cart here. Okay, so whenever there's something like unusual, that's called like an anomaly. And in this case, this golf cart here is anomaly. It shouldn't be here. And that's a very interesting problem because, and it's not just like a problem in image domain, this also applies to like, let's say text domain. You have some sentences and some word comes up which should not be there, right? So that's anomaly in text. Now, how you can use autoencoders to solve this problem, you can have a lot of clean images and you just train your autoencoder on those clean images. Just reconstruct the way we were discussing earlier. Okay. Send as input clean image and you will get the output clean image. Just train it. Now for anomaly detection, what will happen is if you send like some image to the train model, then what will happen is if this network was trained for like, let's say this walkway, then if only clean images were used during training, then this kind of object will be something new for the network because the network has never seen this object. And if the network has never seen this object, it will have a hard time to reconstruct this object. Okay, so we make use of that information. If the reconstruction is actually bad, the model is failing, then we can say that, okay, something wrong is going on here. All right. So those were like some simple applications, and I think very, very powerful applications. We do have those like in real world today in a lot of different applications. So some of the properties is like your autoencoders, once they are trained on some data, they're kind of data specific. For example, if you're training your autoencoder on, let's say, outdoor images, then that autoencoder will not work for indoor images. Okay, so it's kind of data specific, and that's not very specific to autoencoders. That's like a property of most of the deep learning models. You have some kind of domain shift, the models will fail. The other thing is the reconstruction. I mean, it could be one good application, but most of the times it's kind of lossy because we are losing a lot of information. I showed you one example, right, where we were compressing into just 2 numbers and just trying to reconstruct. But again, the shape was preserved, but the fine level details, for example, logo on your T-shirt, that was gone. So if we are merely going to use it for high quality reconstruction, then we'll have to do something else to actually avoid this loss. Now the good thing is it's very easy to train. All you need is just data. You don't have to have like any labels. And if your testing scenario is like or from the same domain, you have similar kind of examples, it's going to work pretty well. But for out of distribution samples, it might not work